So in this video, we're going to continue with chapter 1, and we're going to talk about matter in this video. If I was to define chemistry, and there's different slightly worded definitions, but essentially it's the study of matter. So the study of the composition, structure, properties, and transformations of matter. So since chemistry is the study of matter, we should probably talk a little bit about matter, right? That's what we're here for. If we were to define matter, matter is defined as anything that has mass or occupies space. Which, if you were to then insert that definition into my definition of chemistry, essentially chemistry is a really broad field, right? The study of the composition, structure, properties, and transformations of anything that has mass or occupies space. Which is why we break chemistry into lots of different fields, right? We're in general chemistry, which is a little bit about everything, right? General doesn't mean easy, it means general. So we'll have some thermodynamics and kinetics and acid-base stuff in general chemistry 2. In general chemistry 1, we really just lay the foundation for all of that. Organic chemistry, biochemistry, which is what my degree is in, and so on. Nuclear chemistry, electrochemistry, I could go on. It's a really incredibly broad field. Since this is general, it lays the groundwork for all of those other branches of chemistry. So the study of the composition, structure, properties, and transformations of anything that has mass or occupies space. We are going to classify matter, so classifications of matter. And as I said at the beginning of the first chapter, or the first video of this chapter, this should all be review. So classifications of matter, hopefully you guys know that we have pure substances. And then I'm going to write some stuff under it, so I'm going to leave a little space. And then over here, I'm going to put mixtures. Sometimes I feel it's easier to define something if you can compare and contrast it to the other, so I want to do that. I'm actually going to do a mixture first. So what a mixture is it's a physical, and we will review the difference between physical and chemical properties here in a little bit too, but it's a physical combination of two or more substances. So if I was to take salt and put it in water, all I'm doing is physically combining them. Salt still has all the properties of salt, water still has the properties of water, they just happen to be in the same container. If I was to take a beaker and put M&Ms and Skittles in it, it's a mixture, right? I have a physical combination of Skittles and M&Ms. They haven't chemically combined to form something new, they're just physically in the same container. So a physical combination of two or more substances. Each of those substances retains its individual properties. And I'm going to come back to that definition when we talk about one of our types of pure substances. A compound is going to be one of our types, and it's often really confused with a mixture. Generally, it's the question that most people get wrong on my first test. So pay particular attention to that difference. A pure substance is just that. It's a single type of substance. There's two types, and I think it's easier when we go through them. Our first one is an element. And an element is made up of a single type of atom. If you were to take matter and break it down into the smallest type, we would have, if you just break it down smaller and smaller and smaller and smaller until you get like an individual particle that has those properties, we would end up with an atom. An element is made up of a single type of atom. And we will review atoms also, I promise. We'll spend actually quite a bit of time on atoms. So made of a single type of atom. It doesn't have to be one atom, it just needs to be a single type of atom. Remember that some substances exist as diatomic elements, and we'll review that also. Our second one is a compound. And a compound is made of two or more different types of atoms that are chemically combined. So this is where it can get kind of confusing, right? If I go back and look at my definition for a mixture over here, right? These guys are physical combinations. These are chemical combinations. The other part that I'm going to add is that the properties of the compound are different than the properties of the elements that were combined to form it. Right? If we go back up here, each substance retains its property. Here, my properties are different than what we started out with. A compound is something entirely new. So we took atoms of different elements, we combined them to make a pure substance. Remember, these are our pure substances here. It's something completely new. It's not like I took two things and put them in the same container. The example that I usually use is if I was to make sodium chloride, which is if we think table salt, I take a sodium atom, so Na is our abbreviation for sodium, and then I take a chlorine atom, Cl is our abbreviation for chlorine, and I put it together, I make sodium chloride. So essentially, table salt. Right, this is my compound. If I was to make a mixture, I would have sodium atoms and chloride atoms, or chlorine atoms, in the same container, but I wouldn't chemically combining them. So separate, right, before I make a mixture out of it, I guess we can keep the same color here. Sodium is a metal. And it actually will catch on fire. It's not very dramatic, but it will spark when it gets wet. I used to manage a chemical storeroom, and we would have to keep our sodium metal under oil, so that way the humidity from the air, this was in Michigan, not Arizona, so it was quite humid, the humidity from the air could cause it to catch on fire. So sodium is a metal that catches on fire when it gets wet. Chlorine by itself is actually diatomic, so I'm going to put the 2 there. This is a poisonous gas. Poisonous gas. If you breathe it in, you will die, right? So I'm taking sodium, a metal that catches on fire when it gets wet. I'm taking a poisonous gas. I'm chemically combining them, right, because I'm going to make a compound, and I end up with table salt, right? The properties of table salt are completely different than the properties of sodium and chlorine when they were separate. So I'm making something entirely new. I'm chemically combining them, right? My mixture, if I wanted to make a mixture of sodium and chloride, I could. I would just have a poisonous gas and a metal that catches on fire when it gets wet in the same container, right? They keep those properties. When I make a compound out of those same 2 things, I'm making something entirely different. So I do want to talk a little bit more about elements. Right? Elements were our first type of pure substance above. We said they were made up of only a single type of atom. We can go out and look at our course periodic table here, and each square on here, right, each symbol represents a different element. So H is hydrogen. Hydrogen is made up only of hydrogen atoms. If I go over here, O is oxygen. Oxygen is only made up of oxygen atoms, right? A single type of atom make them up. Gold. Gold is only made up of gold atoms. Do note that we're using symbols to represent them on our periodic table, and then often when we write them, we also use symbols. Right? When I was writing the compound sodium chloride above, I used the symbol for sodium and the symbol for chlorine. So 1 to 2 letter symbols. So if I say write the atomic symbol for something, this is what I'm talking about. I am very particular about how you write them, and I want you, the way that I'm particular is I want you to write them correctly. So I'm going to go back out to that periodic table again so we can take a look at it. If there's 2 letters, the first letter is always going to be capitalized, and then the second letter is always going to be lowercase. So if we look at sodium here, capital N, lowercase a. Beryllium, capital B, lowercase e. If it's 1 letter, like hydrogen, then it's always going to be capitalized. I am going to grade you based on that capitalization. So even if you're handwriting, and you don't get to use it as an excuse because my handwriting is like this, where I often write capital letters for lowercase letters in the middle of a name. We have elements right here. So I have a capital E and I have a capital E. Sometimes I write them as lowercase, but more often than not, I write them as capital. Here it's lowercase. But when I'm going to write the symbol, right, the atomic symbol for something, so let's say iron. Iron has the atomic symbol of Fe. I'm always going to write it lowercase. If I was to write it this way, I'm not writing it correctly because that is not my symbol, right? If I was to do this and say that that is the symbol for a plus sign, I would be incorrect, right? That's a minus or a dash, that's a plus sign. So symbols do need to be written correctly, so do be careful on that. I want you guys to have, to get into the habit of writing them. My R's are another one. If we go back up and find an R, I'm sure they're here. Here I have an R, it's capitaled, right? Here it's capital. Not that you can tell from my handwriting, but that is a capital R. If I was to write the symbol for chromium, I am going to write it lowercase because that's the proper way to make our symbol. So 1 to 2 letter abbreviations, first letter capitalized, second letter, if there is one, is going to be lowercase. And it's also good form to try to get in the habit of actually saying the name of that symbol. Like if I write down Fe, I'm not going to say Fe, I'm going to say iron, right? Because Fe is the symbol for iron. So if I put that plus sign down, I'm going to say it's a plus sign. I'm not going to say it's a horizontal line with a vertical line going through the middle of it, right? I'm going to say what it is. I know I'm harping, sorry. I have pet peeves and this is one of them. If you don't know it, or if you go back to the periodic table, sorry, I'm jumping around on you, like this one, oops, need a pen. TB, I honestly don't know what that one is neither, so I'm going to say TB. But if you know what it is, and you should know the common ones, then you should say the name of the element, not the letters that make up that symbol. For example, Dr. Blake. It's another chemistry instructor in our department. He has his doctorate. And if I was to write his name and then say that out loud, I'm going to say Dr. Blake. I'm not going to say Dr. Blake, right? Dr. are the letters that I wrote down for the abbreviation for doctor, but then when I say it out loud, I'm not going to say Dr. Blake. I'm going to say doctor. So if I write down Fe, I'm going to say iron. If I write down H, I'm going to say hydrogen. If I write down O, I'm not going to say O, I'm going to say oxygen because it's the abbreviation for oxygen. So it's just really good form to try to get in the habit of saying the word that the symbol represents, not the letters that make up that symbol. And again, if you don't know it, that's fine. You can't say the name of it if you don't know what the name is. But for the more common ones, it's really good form. If you guys are going to go on particularly and take more chemistry, you want to, sound like you know what you're talking about. Say the name of the element, not the letters that make up the abbreviation. Okay, get off my soapbox now and move on. I did mention that some elements exist as diatomic. So di means two. So two atoms. Two of the same atom. Remember, elements are made up of a single atom type. If it was two different elements, then it would be a compound, not an element. But some do exist as more than one of the same atom together. And I do want you to know those ones. So hydrogen exists by itself as a diatomic, so H2. You're not going to find a single hydrogen atom all by itself out there. It's going to be two of them that are chemically combined. Because it's hydrogen and hydrogen, it's still an element, right? A single type of atom. Hydrogen, let's go to the periodic table and we'll just point them out there. That might be easier. I'll write them down also. Let me erase some of this stuff. The way that I remember them is that they form a 7, and there's 7 of them. There's some mnemonics for it, but this one actually works better for me. So hydrogen, it's kind of displaced, but then you go over here, nitrogen, oxygen, fluorine, and oops, I didn't know it would do that. Nitrogen, oxygen, fluorine, and then chlorine, bromine, iodine. So this makes like over here like a little 7. But then if you count, there's 1, 2, 3, 4, 5, 6. We know there needs to be 7, so then you remember that hydrogen's over there. So those ones exist in nature as two of the same type of atom bonded to each other. So hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodide. Sulfur actually exists as 6 of them together. It's not just one sulfur atom. It's S6. There's a few others that are kind of strange like that too. But do you know these diatomic ones? If you've forgotten them from the past, then you want to refresh your memory. So if I just say oxygen, I'm going to write O2. If I say an oxygen atom, and I'll try to be very specific about it, then I'm going to write O, because I just want an atom, not the element itself. So as an element, that's how these are going to exist. I do want to go back to mixtures real quickly. Remember, mixtures were our second type of classification of matter, right? We had pure substances, under that elements, which we just talked about, and compounds. Mixtures were the ones that we said that were physical combinations. We can actually separate a mixture into the components that make it up using physical means. You would need chemical means to separate our compound. Remember, when we make a compound, we're making something entirely new. It's a chemical combination. Under mixtures, though, there are 2 types, heterogeneous, and these are in no particular order. It's an S, and then homogeneous or homogeneous. And they both are mixtures. They both are physical combinations of 2 or more different things. Really, the only difference between these two is how it looks to you. So a heterogeneous mixture is a mixture that looks like a mixture. If you look at it, it's obvious that there's 2 or more different things combined. If I was to take a whole bunch of dice and some marbles and put them into a container, it looks like marbles and dice together in a mixture. It looks like more than one thing mixed together. Something that's homogeneous or homogeneous doesn't look like a mixture. So if I was to take table salt, sodium chloride, and add it to water, it just looks like water. It doesn't look like there's a mixture in there. So heterogeneous, this is a non-uniform composition. So it's a mixture that actually looks like a mixture. Homogeneous has a uniform composition. It actually doesn't look like a mixture, even though it is. A typical example that I usually use for homogeneous is Kool-Aid. If I was to take sugar, Kool-Aid powder, water, and mix it all together, I have this, depending on what flavor I use, but let's say cherry, I have this red liquid. It doesn't look like I took 3 different things and mixed them together. And again, it's a physical combination. The Kool-Aid powder still has all the properties of Kool-Aid powder, and the sugar still has the properties of sugar, and water has the properties of water. I've just physically combined them. Heterogeneous, we could use, I don't know, vegetable soup. Unless you puree it, then it's homogeneous. We just keep it in its normal form. All right, I have chunks of potatoes and carrots and green beans, maybe some lentils, depending on what you like in your vegetable soup, but you look at it and it looks like a mixture of different things. So both of the mixtures, one happens to look like it, the other not so much. But do know that it's still a mixture. It's still a physical combination where the components retain their own individual properties.